Welcome back, everybody. Tonight what I want to cover is conservation of energy. When we think about conservation, in typical terms, we think of conservation of natural resources. Why do we need to conserve natural resources? Well, we have a finite supply of oil and natural gas and certain minerals that are found in the Earth's crust. And if we use them all up or convert them to a form that is no longer useful to us, then we don't have any more of those resources left. So it is important to conserve them. The idea of conservation comes along with the concept that when something is conserved, the total amount of that quantity remains constant. In the context of energy, what that means to us is that we have a certain amount of energy total that's available. And that energy could take many different forms. It could be kinetic energy, or it could be potential energy, or heat energy, or chemical energy, radiant energy, nuclear energy. But the idea is that you have a total set amount. You can basically take that total amount and convert it into various forms, but the total amount remains constant. Energy is conserved as long as you have certain constraints on your system. So I'm going to show you a quick video illustration that sort of hopefully makes this point. Alright, today's topic is conservation of energy, and I have asked my lovely advisee, Katie Daniels, to assist me in this demonstration. So when we talk about conservation of energy, we're talking about something that is conserved or remains the same. So I'm going to ask Katie to hold up the cup of M&Ms that I have given her, and the M&Ms in this cup represent energy. There's only a certain number, it's a finite amount, and if they're conserved, that number has to stay the same. So let me set the scene for you. Let's say you've decided that you want to climb to the top of a hill. So you're going to have to exert some force to climb to the top of that hill. You're going to have to move through a distance. That's work. And so Katie is going to take some of that energy that's available and she's going to do work. So she's used all of her energy. She has now climbed to the top of a hill, done work, and she has now done work to convert that into potential energy. Symbol is PE. It's energy relative to position. So now all her energy has been poured into potential energy. But of course, at the end of the day, she needs to go back down. So let's say she decides to roll down the hill. So she is going to now let that potential energy be converted into kinetic energy, energy of motion. Now, realistically, along the way, as she's sliding down that hill, there would be friction present. And so a little bit of that kinetic energy really went into heat and heated up the ground, but not a lot. Most of it was converted into kinetic energy, and she had speed when she hit the bottom of the hill. Bottom line, you have a set amount of energy. You can convert it from one to another, just like Katie could pour M&Ms from one cup to another, but the total number stays the same. Thank you, Katie. And now we're back. So another question might be, why is this useful to us? What good does it do to have a law of conservation of energy? How can it help us with analyzing the types of situations that we're typically dealing with in physics? I'll give you an example. Let's say we have a problem like this, where we have a 30 kilograms child who is sitting at the top of a 5-meter tall playground slide. And if we ignore friction and we ignore air resistance, then what we want to determine is how fast will that child be moving when she gets to the bottom of the slide. Well, if we try to analyze this with the tools that we have so far in our physics toolbox, that would be kinematics equations or Newton's law type analysis, where we would have to look at the forces involved and determine the net force on the child, determine her acceleration, maybe know how long the slide was. Let me draw a couple of things on here that we might need to be taking a look at. For instance, if I were trying to do this with forces, and we thought of the child and drew the free body diagram forces type that were to act on the child, we of course would have gravity acting straight down toward the earth. So label that force due to gravity. And then we've got normal force that acts at an angle perpendicular to the slide here. And why is the child coming down the slide in the first place? It's because this gravity vector has a component that acts down the slide. Well, if we really wanted to figure out what that vector, the magnitude of it was, I'm going to go over and switch colors. We would also need to know, for instance, the angle that the slide made with the ground. So if I kind of sketch that in here, I've got this part of the slide, and then here's ground level. And so I'd need to know what is that angle theta that the slide makes with the ground. And all of a sudden this problem sort of got complicated. We'd need to use some trig in order to solve it. It's just a little more tedious. There must be an easier way, and in fact, there is. So let's take a look at what that might be. If we look at conservation of energy in this problem, the energy the child has at the top of the slide is a given amount. That's going to be the same amount of energy that she ends up with at the bottom of the slide. So let's take a look at the step-by-step. So step number 1 here, I said that the total energy that she has at the top of the slide is going to be equal to the total energy she has at the bottom of the slide. As long as we're ignoring friction and air resistance, which would be absorbing some of that energy. I mean, think about it. If you go down a slide, you do lose a little bit of the energy due to friction between, your thighs and your rear end that are in contact with the slide surface. There's a little bit of friction energy there, a little bit of heat that's lost as you go down. But we're ignoring that. So we're going to say the total energy she has at the top is equal to the total energy at the bottom. Now, what would that energy be? At the top of the slide, she's got energy due to her position above ground level. As she slides down the slide, she loses that as she gets closer and closer to the ground, but she's also speeding up. When she gets to the bottom of the slide, she has kinetic energy. Let's take a look at the second equation, where I wrote down the types of energy available. At the top of the slide, she definitely has potential energy, but she's not moving yet, so we could say that her kinetic energy at the top of the slide zeroes out. Yay, that's always a happy thought. At the bottom of the slide, now she's at ground level, so she has zero potential energy at the bottom of the slide, but she's certainly moving, so she does have kinetic energy at the bottom of the slide. Okay, so now if we break it down and we look at the equations that we need to use to calculate those various quantities, I've got for potential energy at the top of the slide, it's her mass times the acceleration due to gravity times the height at the top of the slide. And I'm going to set that equal to the equation for kinetic energy, 1/2 times the mass times her speed at the bottom of the slide, and that quantity squared. That's the speed that we're looking for. Well, before we go further, let's look at one kind of neat thing that happens here. Notice on both sides of the equation, I've got mass. And this is the child's mass. It's the same variable on both sides of the equation. So again, another happy thing happens. I can cancel out the mass. Sort of a neat concept. It means that the speed this child has at the bottom of the slide is independent of her mass. In other words, her father, who might be at the playground with her and who she persuades to go down the slide, would have the same speed at the bottom of that slide as she would. Or even if she has a little brother who's like a toddler, 3 or 4 years old, who's probably less massive than she is, he would have the same speed at the bottom of the slide. So it's kind of neat, independent of the mass. Now let's look at actually plugging and chugging, put the numbers in. First of all, I did the algebra to solve for the speed, and that meant I multiplied both sides of the equation by 2. So I ended up with 2 times the acceleration due to gravity times the height, took the square root
raised it to the 1/2 power in order to take the square root of that. Plug in the numbers. 2 times 9.8 meters per second squared times the height of the slide, which was 5 meters, and then take the square root, and I get for an answer 9.9 meters per second. Pretty nice. No angles, no trig. You gotta love conservation of energy. Thanks for watching.